Hello community, so great that you're back. Let's do science and let's do AI for science. Yes, absolutely. And the first paper of today, September 23rd, says AI models are using materials from retracted scientific papers. And then it said, okay, yes, okay, and MIT tested this, yes, and all the things that you use here normally, like Perplexity or something, yes, it uses here the answer of retracted scientific papers without telling you, the user, hey, those papers have been retracted. I sell you some scientific information that is not anymore in the body of the scientific knowledge. But come on, who cares about this? No, let's do AI for science. Yeah, this is just a surface problem, no? But we want to go deeper. We want to go here really and have AI think like a human scientist, no? And what we want, what we all dream of is, aha, I see a new pattern here after looking at thousands and thousands of research data, and says, a new rule that no one has noticed before. I, the AI system, I see it. And this is the dream of every scientist. You just provide the experimental data, and AI does this thinking for you and shows you, hey, those are all the patterns that I found in this data. And this ability to infer general rules from specific example we call inductive reasoning. And this is at the very heart of a scientific method, and you want AI to do this in science. Find the rules behind the data. Find the patterns. Now, if you want, the camp of LLM reasoning is split now, no? We have those we call equation seekers, no? Those people test the LLMs on their ability to discover physical laws that can be described by symbolic mathematical equations. And this is, if you want, a form of symbolic regression. But there's also the other people with abstract puzzles. No? They test here for this induction using here synthetic puzzles. So this is great, but you know what? There is something in between. And we have today a brand new study where the authors say, you know, there's more to this than this. So let's have a look. Because the authors tell us there's a big delta. Can our large language model perform scientific inductive reasoning when the rules are not neat mathematical formulas, but are hidden here in tons of data? And you might say, of course, I mean, even on my channel, just look, 10 days ago, I had a video about AI scientist, or here, the Google Stanford co-scientist 7 months ago, or 2 months ago, AI breaks science, or the truth about AI. This is such a hype topic, AI and science. And therefore, a much needed dose of realism is now needed here in this field, AI for science. So therefore, I want to show you a brand new study. And this new archive paper is now, if you want, a corrective to the narrative that LLMs are on the cusp of becoming autonomous scientific discoverers, beautiful, super intelligence by Meta. Oh, this sounds so great. But you know what? The reality is completely different. And I know that I have videos here about deep scholar and everything, but today we're not going for deep scholar knowledge. We are going here for the inductive reasoning process. And you know, we do have benchmarks like Reasoning Gym, no? But this is all really limited. You might say, hey, wait a minute, here, September 22nd, we have a brand new study about the reasoning core, a scalable reinforcement learning environment for symbolic reasoning. Yeah, absolutely. So here we have a new paper where we can, if you want, explore the core cognitive capabilities that are now transferable to real-world problems, then this constrained rule-based cleverness. Yeah, but let's go one step further. So this reasoning core is great for symbolic inductive reasoning, for causal reasoning via the Bayesian network or system equation solving. This is all great if you have external solver, but what about here the internal capabilities? And they give us here a beautiful indicator. Let's see, in orange we have GPT-5, then we have GPT-5 Mini and GPT-5 Nano. And they compare to the performance, 0 to 100%, for a set of different tasks. And let's just look here at equation system. And you see with GPT-5 Nano, we are below 50%. With GPT-5 Mini, we are at 50%. And with the full GPT-5, we are above 50%. Sounds great, but let's have a look here at reasoning. With Nano, we are below 25%. With Mini, we are above 50%. And with GPT-5, we are at 75%. Look at this spread. What is going on? Is it really just scaling? Or is scaling just a wrong indicator? Is there something else hiding behind those data? And therefore, a brand new study, this is the main study of the video, this is here already from September 12, 2025, LLM-based scientific inductive reasoning beyond equation. It was published today, by the way. And they here beautifully have a simple question. Huh? Can we enable our LLMs to learn the underlying patterns from limited examples in context learning? You would say, yes, absolutely, in entire novel environments and apply them effectively. So nothing from the memory of the LLM, of our agents. This is really, you are pushed with your knowledge in a new environment and you have to do as an AI reasoning. And you cannot rely on patterns that you know from other environments. This is now, does abstract reasoning exist? Think about your code. Do you just resurface here code that was written before you by thousands and thousands of other coders? Or is there something new? Is there some new brilliant code line that you can use now with AI coding LLMs? So the authors of today's study said, let's evaluate now the inductive reasoning abilities of LLMs in the scientific setting and think, come on, let's go beyond mathematical equation discovery. We want to go for the abstract reasoning. And they built a benchmark here of 710 instances, biology and chemistry, about chemical reaction, molecular structure. And I will show you those tests here. This is really simple test. And they say, and now in this task, we want to involve here inferring non-mathematical rules from in-context learning. So what is now more dominant? The parametric knowledge of the LLM, the inherent knowledge, or the in-context learning for reasoning? And we do this now here for inductive reasoning. And there's the beautiful number of 7. And yes, 7 is 7 tasks across 2 scientific domains, especially designed here to be unsolvable by simple mathematical formulas. You have to reason. And the authors tell us here, they have here beautiful examples about DNA translation, DNA table inference, and DNA transformation, plus about molecular design, molecular captioning, reaction prediction. So an implicit understanding of some complex chemical reaction mechanism is needed to solve those very simple tasks for a human, and even some name prediction. Couldn't be easier, no? Smiles. If you will see this, we have the biological task and the chemistry task, definitely science task. And let's see what happens if we provide in-context examples here to the LLM for reasoning. Oh yeah, 4. Another beautiful number is 4, because there are 4 different prompting strategies. Because you might say, yeah, but come on, this prompt is not professional, no? You have to go with GPT-5 prompt optimization, no, and whatever. So they say, okay, we go with 4 different prompting strategies for each and every model to really understand LLM reasoning algorithms, and then we can test what is the best LLM reasoning implementation like React or whatever we have to see what mechanism helps us here for inductive scientific reasoning. And they say, okay, so let's have a look. So what we have inductive reasoning, the implicit part. And we have inductive reasoning, the explicit part. Now, implicit is the simplest one. Huh? You just say, hey, simple approach. The prompt includes a few in-context examples, 3, 4, 5 examples, followed here by the test query. No? And the model is expected to infer here this new pattern implicitly from the data and provide you a direct answer. Now, explicit, very simple. It's also prompted here to explicitly write down the hypothesis of our AI or the rules the AI thinks it discovered in this data, see that it has inferred from these examples given in ICL, and then it is asked to apply that hypothesis to the test query. So you see, we reduce the complexity and we say, okay, we separate these. We make it really baby easy. We separate here the induction step from the deduction steps in the reasoning process. And then, of course, we are interested in a little bit more advanced reasoning, the self-consistency. This improves robustness. Everybody knows this, no? And now we run the same model multiple times. We are here next token prediction, here probability, to generate several different explicit hypotheses. And then we just have within the AI a majority vote to vote for the best answer. But of course, the real interesting part is hypothesis refinement. No? The most sophisticated strategy, the authors tell us here, for an iterative scientific progress process and they say, okay, at first we generate it, then we select it, then we refine it, then we repeat it. So we want to go here with the best refined hypothesis this system can find if we have runs and run and we let the system think and we give time to the system, no problem at all. But then we have the best hypothesis, hopefully found by the AI system. This is the beautiful number 4. So what are the key findings here from this paper? What is it that we detect? Here we have it again. So here we have models, and yes, they are not the latest model. We have a Claude 3.5, and you know why we have not the latest model? Imagine here somebody from a university would say, hey, those commercial models from the global corporation, they do not perform like the marketing brochure tells us. So of course, every responsible scientist takes here an out-of-generation model to get not into any legal troubles. And maybe you want to have some funding now from this global corporation for your university. So this would be really stupid here to go for the latest one. So, but you know what? Yeah, you will see the trend. Again, we have here the test, biology, chemistry, 3, 4, 7, and then here the 4, 1, 2, 3, 4. And now let's have a look at the results. This is now absolutely interesting, and just go for the average. We will have a deep dive a little bit later. You do a deep dive if you read this. Look at the average, what's happening with Gemini 2.5 Flash. Here on average, we have here for the implicit 43%. For the explicit, 38%. And you might say it's strange. Why is it here dropping here in the performance just by writing out here its own hypothesis it has internally? But look at this. If we have hypothesis refinement, where you really give it time, it runs and optimizes itself, we just move from 38.6 to 39.0. What? You might say, so you know what this means? This means the bottleneck is not in the refinement of the thought process, of the chain of thought. You have to give it time. You have to make it think about it. Look, this is just neglectable, the jump. It is informing the correct hypothesis, the correct one, in the very first place. You have to have the power of reasoning. It's just not about just try out as you want. Absolutely fascinating that you can deduct this here from these simple results. But let's look at this. There's another beautiful idea that he had here with the delta. No, we talked about this. There's a performance gap if you have here calculated as the score on syntactic task minus the score on real authentic task. Remember, this is a benchmark and we want to just focus on one part here on the inductive reasoning part. So they say, great. So we have now to build a diagnostic tool, the authors tell us, that separates now the true reasoning from a pure mere recalling from the parametric knowledge of the LLM. If the LLM has seen by chance some of the task in its pre-training dataset, then it knows the solution. So you want to make sure that with some syntactic tasks that are a little bit crazy because they have to be out of this world, no? But within the scientific domain. So you create now a novel syntactic genetic code that has not been published yet or not found yet. So the authors remove now the possibility for the AI system, for the LLM or VLM, to rely on its vast store of memorized knowledge, the parametric knowledge inside of the AI system, because now we want to see, is it really learning from in-context example of syntactic code or of syntactic scientific data? Is it really now performing a genuine induction from the in-context example provided here for the reasoning process? And here you have it. GPT 4.1, indicative for the GPT family. You lose suddenly if you do this. If you look only for the real reasoning part, you jump from 81% down to 12. So you lose almost 70% of the performance, 70 percentage points. And for Gemini 2.5 Flash, you fall down from 87 to 32%. So much about the inherent reasoning capabilities. Because it looks suddenly with this particular syntactic task and test that they provide, like the system somehow has found a similar pre-training dataset task here. So it already has somewhere in its memory a solution from the pre-training data. It was not reasoning itself. It was just looking up, let's say, in the complete internet. And the authors here, okay, this is a little bit more official. The authors say, this result strongly suggests that when LLMs perform well on scientific tasks in our old-fashioned benchmark up until now, no? They are often not reasoning from first principle, but instead they are accessing here a high-fidelity memory of information they saw during their pre-training, fine-tuning, reinforcement learning training, whatever. But when we design it in a particular way in an experiment where we say the LLM memory is simply made useless by our configuration, or by changing here the rules for a synthetic genetic code, then the true, much weaker inductive capabilities are exposed. Therefore, the authors say memorization over reasoning is currently the topic in our LLMs. They don't reason. They just recall memorized facts from the training data. And then let's come, because remember 4. 4 is the other number. And they say the performance gain from using here, 3 and 4, the self-consistency prompting methodology, and the hypothesis refinement, the iterative loop refinement. They say the gains from those were minimal and inconsistent. And if you look at the data, in some cases, they even hurt their performance. Because for Gemini 2.5 Flash, the average score dropped even from 43 to 39%, suggesting that forcing the model to explicitly reason now within context learning can sometimes derail its fragile inductive process, and the model loses performance when doing in-context learning with a few short learning examples. So you want the LLM to learn new knowledge, and the LLM even forgets more of its existing knowledge and does not even learn the new presented datasets. And then there's something that they say, what about context length? Is it still a topic in 2025? Come on. I've seen now models with 2 million up to 5 million token context length. And they say, wow, we don't have to go to 1 million. Come on. In a task like in a DNA transformation, the model performance dropped in our particular experiment significantly as the length of the DNA sequence strength increased, showing that the ability to induce patterns, to find those DNA patterns in tons and tons of data, it weakens over longer context. So yeah, context length, much below 1 million context token, is still a challenge for today's AI. And I love this test because it brings us back in reality. We only read in the internet and hear in the marketing from the global corporation, oh, super intelligence and what the heck. It is all not grounded in reality. And they say, therefore, our LLMs often fall back on what these models memorized during the training instead of performing here true reasoning from the evidence presented. And it's a beautiful example here. Have a look at this paper. I think this new archive paper really brilliantly illuminates here that there's a difference between an AI that knows science, and don't get me wrong, our current LLM, they are like a librarian, no? They have extreme passive knowledge. But you know what? It has nothing to do with an AI that can actively do science. Those are two different worlds, and our LLMs fail exactly at this boundary. So, whenever you see an AI knows something about science, does not mean automatically that it can do science. This is a different class of patterns for our AI system. And the authors conclude, you know what? Inductive reasoning in our current AI system is a fundamental weakness. And current state-of-the-art LLMs are fundamentally limited in their ability to perform genuine scientific induction in complex non-mathematical domains where we just have a simple mathematical formula that we can reference then here with external solver over agentic systems. So the core of your agent, your LLM, is fundamentally limited in the ability to perform genuine scientific induction. It cannot reason in the complexity. It can paste and copy what it learned, but it cannot do scientific induction. And therefore, I think this is nice because this paper is a positive paper. It shows us there are limitations. Hey, AI is going to be fascinating in the next month and years because it is not working. This means we have to build a better AI. We have to think about it. We have to design better AI systems. We have to come up with better solution for this process. And it's not what you might think simply scaling up here the existing models or even more complex prompting schemes or DSPy squared. No, this is not the way forward. Yes, you can get a little bit of a performance jump, but it is inherently systematic, limited. So what we may need instead is explore fundamentally new architectures and training paradigms that better equip the next generation of models for the abstraction, for the causal inference, and the true hypothesis generation that we need in science now for inductive reasoning. Because this is exactly what we want to do. This is what we need for our research work. We need an AI companion that is able to have this inductive reasoning capabilities. Otherwise, we humans are just beautiful ourselves. I hope you enjoyed this video. Hey, why not subscribe, and I'll see you in my next one.